Welcome to the 101st colloquium of the School of Astrophysics after the 100th colloquium last week. We are very glad to have Professor Orko Sharangi from Indian Institute of Astrophysics in Bengaluru as our speaker today. So like many of the School of Astrophysics colloquium speakers, Orko is also an alumnus of the Erstwhile Presidency College Physics Department. So he was here from 2005 to 2008. So after his BSc, he went to IIT Bombay for his master's and then to University of Basel in Switzerland for his PhD. And then he was a postdoc at Goddard, NASA Goddard Space Flight Center for 4 years. And then he was a postdoc and then an assistant professor in the Niels Bohr Institute in Copenhagen. And then he came back to India and became a faculty member at IIA in 2024. So Orko works on something that we all wanted to play with when we were kids, but our parents always said that don't play in the dust. But so Orko decided to work on astronomical dust so that no one can stop him. And so that's what he's going to talk about. Incidentally, maybe it is not an accident that I taught interstellar medium and dust this morning to the first year students. So I'm expecting a lot of questions and answers from them and others. And so Orko has worked with JWST data and some simulations about production of dust in the interstellar medium and evolution of it. And as you know, in recent JWST observation, dust has become very important. Probably the most important that dust has ever been, because it can make and break various theories of galaxy formation based on what kind of dust they have and don't have. So without further delay, let's hear from Orko about dust. Yes, very accurate.
Okay, thanks a lot. It is wonderful. I mean, it's like almost a dream to be here as a speaker from where like I was made once almost 16, 17 years back. Which the one on the top? Okay. Yeah, so I will talk on like how cosmic dust evolves in galaxy, but I'll try to make it as pedagogical as possible, because once you get the framework, you would be able to proceed with it in different aspects of research. But first we have to understand the importance of it, and that should be my goal of what I want to achieve at the end of the talk. And of these people who are working on like last 2-3 years since I moved to India, I have been associated with PhD students, postdocs, or researchers. So these are the people who have been contributing to a lot of things I will be talking about. So I would obviously want to acknowledge them. So if you look at a typical galaxy, like you will see an image like that we expect, right? So in that, what do we see? We see some bright spots which comes from stars, and there are some dark patches all around. Now, if you take up the mass of all the baryonic mass that is present in a galaxy, then all the stars make up of most of it, while 1 to 2% of it, which is very small in number, actually constitutes the gas and dust that is present in these patches. All these points that you see, bright ones, are star clusters and stars of different types and all that. While if you in that picture, you may feel like, okay, so gas and dust, are they at all important or in terms of contribution to what a galaxy makes? To understand that, we have to actually look at what happens when light passes through it. So to make that more into context, maybe I have another slide later, but even if in mass they actually occupy a very small fraction of mass of the galaxy, in volume they do occupy a large part. So in cross section, a large part of the cross section in our galaxy is occupied by gas and dust clouds. So now how do they become important in astronomy? When light passes through them, they can be either absorbed or scattered, that photons, through when they are passing through any kind of gas cloud. And then when it does, because of different scattering laws, you will have selection effects on which part of the wavelength spectrum will get scattered more, scattered less. And as you know that red part of the sky is scattered less, and so when any kind of starlight or any light from a distant galaxy is passing through a cloud, it often scatters selectively or absorbs selectively. So you will receive a light which is relatively redder than what you would see without that cloud. So as this picture shows, this is a molecular cloud. And if you see that image in optical wavelengths, you will see that this is a historical image, because I think Sir William Herschel noted them as like holes in the heaven, because they were actually surprised to see there are dark patches with nothing in there. But then very soon after that, people actually realized that they are not actually voids in the space, but they are filled with so much material that light cannot pass through. But in the same region, if you probe that in a different wavelength, as you see an infrared image of the same dust cloud, you will see that there are bright stars right behind it, and they are visible in those wavelengths because of the principle that red light will pass through you more easily than blue light or the starlight mainly. So summing up all of these together, if we just take a galaxy and take its spectral energy distribution, you will see that all these stellar contribution, a large part of it gets absorbed by these clouds, and this shaded region you see here, these are actually absorbed all by gas and dust, and then they get re-radiated in the infrared and submillimeter bands. And so in a galactic spectra, a large part of the energy is actually coming in these wavelengths. And once you understand how to read them, how to make an analysis of them, you would actually get a lot of information of the galaxy or the any other astrophysical object itself, just by looking at the properties of what is happening due to the emission that is coming from these dust and gas clouds in galaxies. This is like from a scientific perspective. With that, if you just look at a cloud which looks like that, you have all seen images like that. Hubble Space Telescope is like popular for taking amazing pictures of our galaxy or neighboring galaxies, and lot of images are actually from these molecular clouds or nebula that we see in. What we cannot see is, if we had the scope to zoom in inside further and further and further in these clouds, you would actually see clusters of chemical compounds, the same chemical compounds that are present here in this room. And that is how the nomenclature dust came from, which at all does not sound astrophysical, but it is named in this way because the chemical structures of the dust grains that is present in this room that we cannot see are almost similar to the structures of the chemical compounds that are present in these clouds as well. Of course, we cannot zoom in to atomic scales in these clouds, but there is no denying the fact that there is a lot of it. As I explained, from like just a galaxy perspective, its spectral perspective, and its chemical signature perspective. So there are a lot of these guys present in space. Okay, so then next question, as a physicist, you will ask, where did they come from, or how did it actually happen like that? Is it a part of the galaxy formation, evolution? In what phase of the life of a galaxy does these clouds appear, and how do they evolve, right? So I am not going into the clouds, but we are just looking, just based on pure physics, what does the galaxy offer us? The galaxy offers us interstellar medium and stars. That's what the galaxy is made up of. We go to the stars. Stars are too hot, ionized stuffs all around, and we do not have any environment which would actually let us go through a series of chemical processes that you need to form any dust grain. And that is no surprise there, because we know how chemical compounds are synthesized. It is done in the lab. It is done every day in atmosphere. It is done in sea surfaces. It is done in our clouds. So we have an idea of what type of chemical reactions we expect. But if we go to stars, inside the star is too hot. Even the surface of the star, it is too hot. So we do not have any environment where you can actually make a lab to produce chemical compounds. Fine, I go to the interstellar medium. Temperatures are much low. We have enough time. On the other hand, the challenge is that lot of these reactions actually need energy, and there are activation barriers in any kind of reaction. Many of the reactions need activation energy or barriers to cross through to actually happen, and to form a dust particle, which is a solid particle, from anything in space which is all in gas form, in ionized atoms or say neutral atoms, from a simple neutral atom to grow to a size which is made up of thousands and millions of those solid particles, you need a lot of reactions, and those reactions, many of them requires energy to proceed. We don't have that energy in the interstellar medium. So what is the summary? What I am saying is, in the galaxy there is nothing which is present for eternity that helps us form these molecular clusters which eventually grow to form dust. In this context, we look at the stellar, like the stellar history of a galaxy, where we have stars of different masses, and when they are in main sequence, they evolve and they remain in a similar position for a long period. And what I said about stars, that they are hot, they do not have environments to produce molecules, dust, that remains true. Once these stars move out of their main sequence and become evolved stars, which are all these which are away from the main sequence line, all these evolved stars and ultra star which is on that side, all these stars actually provide us conditions which are sustainable to have chemical reactions in there, which could lead to form larger molecular clusters and dust grains. But as we know, all stars spend 99% of their time on the main sequence line. So this phase, the evolved star phase, see red supergiants, LBVs, which are luminous blue variables, AGV stars, red giant stars, ultra stars, all these stars, what are these? These are the end phase of a star's life. So all these hydrogen burning phase of their star's life, they were on this, and this was 99% of the life of the star. Once those phase is over and the star is nearing the end of its life, in the very end phase, they go through this evolved star phase. But that is a very small period. All these molecular clouds or whatever I am talking about, they must have come somewhere in these regions, but that is only a very small part of star's life. In that way, galaxy's life. So whatever I have to produce, will have to produce in a very time constraint way. And there comes the magic of it, that we do not have a proper channel in which it can very easily proceed to form dust in these molecular clouds, to grow these clouds. We have a very non-equilibrium, very turbulent system where we do not have steady state conditions. Everything is rapidly evolving, and we have to have a lot of chemical reactions in this environment. So this is the structure where we have evolved star environments where the temperatures are very good, densities are high because it is near to the star. We can have chemical reaction, but those chemical reactions cannot happen in a very steady state kind of laboratory kind of environment. So if you apply to what happens in our clouds, when the rain drops condense in the clouds, those principles does not occur in these environments, because the evolution of this medium is much faster than what we have, and the densities are much lower. So if the densities are high, you can have reactions fast enough, but in space densities are low, so you need a certain amount of time, but we do not have that much time. So whatever happens is almost always a race against time. And that is the beauty of it, that in order to explain everything that I talked about, you have a time constraint nature of evolution of physics that you have to understand. Yeah.
You mentioned that the dust in this room and the interstellar dust are similar. Do you mean in terms of sizes or composition also?
In this room, composition would be a little more complex, because you have you have organic compounds are there as well, but because it grows from a very pristine environment, the complexity is lower there. Here you have more complex grains or like dust particles, but yeah, it still constitutes of the silicon, oxygen, carbon, all these things are present here also. It's the same. The complexity could be slightly different, but yeah, some basic ingredients still remains the same. And even I had a picture, I don't have it now in this slide, in under the microscope also the structures are quite similar. Okay, so what I said until now is that we can have stellar environments. Okay, let me actually complete that picture, because I would talk a lot about supernovae. So supernovae are the, I mean, before I even go deeper, there are like supernovae are mostly, there are many channels, but let us assume that massive stars which are larger than 8 solar mass, they evolve and they become red supergiants at some phase of their life, and then they explode and they become supernovae. There are different type of supernovae. I am making it very simple, but this is one of the most well-known supernovae that we find. That stars above 8 solar mass, they go through this channel and finally they die with an explosion, which is supernovae. Now, why does supernova become important in this picture? Because if we go to the very earliest universe, what we'll see that the earliest galaxies which are less than 1 billion years old, they are also very dusty. Okay, so in this context, this importance of supernova comes because only massive stars which are very large in size, maybe larger than 15 solar mass, 20 solar mass, those are the stars which has a very short lifetime, and because of their short lifetime, they are the only one which can evolve fast enough to produce dust. Because as I said, to actually stars to go through this phase, we have to reach the end of their lives. Stars like our sun, which would live 10 billion years, they live for, I mean, they would not be able to reach their end phases within 1 billion year, or even less than that, even 500 million years, where the galaxies are already found to be full of a lot of dust. So the massive stars which actually live say between 10 to 20 million years, those are the perfect ones which would reach their end of their lives by this period, and those are the ones which can only be the sources which can contribute to the like the dusty galaxies that we see when the universe was very very young, within like first 500 million years to 600 million years of the galaxy's life. Those stars, these massive stars, as we see, these are our galactic red supergiants, but say red supergiants in the earliest galaxies, those are the only ones which have enough time to end their life and produce dust. So supernova becomes very important, and it is how the importance of supernova came in the late 1990s. People started realizing that supernovae explosions are one of the major contributors to produce all these molecular clouds and dust clouds that you see around us, because those are the only stars which could evolve and end their lives to produce dust in a very short amount of time. Do we not see them? Is it just a hypothesis? Actually not. Like, I mean, when we look at like supernova, fortunately and unfortunately, they are not very common. We don't see them around happening in our galaxy all the time, but there are a few which we have traced. This one is 1987A. This is one of the most famous supernova which has been studied from the day of its explosion in different capacities. And if we look at it over its age, it from 1994 to 2009, we actually can read clear signs of dust emission, and that is now still in 2023. There, I mean, even if we don't go to the detailed structure, what is this ring, what is this inner face-like structure, all that, but this is part of the star. You can model, you can understand, try to see how the geometry looks like. But nevertheless, one thing is true, that all the parts, these are emission from detected by Herschel, which is a submillimeter telescope, and this one is JWST, which is a mid-IR telescope, and also ALMA, which is a submillimeter telescope. So a lot of these telescopes have been following these objects. I mean, 1994 it was not there. It was mostly studied by HST. But since 2007-8 onwards, it has been studied in different telescopes as well. And we have always seen bright emission from dust present in this supernova remnant. And this is not the only one, but this is one of the most well studied. So there is no like lack of evidence observationally that these supernovae remnants, which comes from massive stars, are full of dust. This is a recent image taken last year of the Crab Nebula, which is a supernova remnant in our galaxy itself. And all these bright patches you see here are basically emission of dust present there. On the other hand, there is a debate that is still going on that, okay, fine, supernova can produce dust, but also it produces a lot of energy, and energy produces shocks and shock waves and high energy radiation. So does they actually not affect the surrounding medium? Which is true. This is an image of a galaxy also taken last year. Yeah, it is also taken last year, and if you see, there are actually patches in the galaxy which are hypothesized to be from supernova remnants, and the supernova remnants are actually sweeping away all the material surrounding it. So what it is doing, whatever was present, all the gas, what dust, what was present in this region, the remnant has actually swept away all that, and they have obviously destroyed a large part of it. So are these supernovae actually producing dust and contributing to the total material you see, or actually they are destroying? So there is a debate, and all these equilibrium, non-equilibrium argument that I was making has to add up to make sense of actually supernovae are producing something, or after the explosion they are actually destroying stuff more in the galaxy. This is an infrared image. Both are
Thanks. Millimeter.
Some, yeah, I don't know which one. Yeah, this is a JWST image. This is Fangs, but I don't know the telescope.
It will just mix the dust, right? Or
No, it will destroy. No, it will destroy a lot, because firstly it has very high energy radiation. Then it will, yeah, it will physically and radiatively destroy a lot of material present in it, around it. JWST image, yeah. Okay, so again, like, are they still hypothetical in from the telescopes, or we can actually see them more closely? If you look at like this sky, this is a cartoon. What is it showing? That our sun is present somewhere here, and our sun is moving all around our galaxy in millions of years. When the sun was moving, there were different dinosaurs in different eras that used to live on Earth, and once they are moving, what is it doing? A star is moving through the Milky Way. What does it mean? It is moving to the interstellar medium, and the interstellar medium is falling on us. So we are actually collecting particles from interstellar medium to fall on us, and those particles are present. Those particles are present on the surface of the moon. Those particles are present in the deep sea. If you go and dig deep sea sediments, you find particles which were present in the interstellar medium millions and millions of years ago. And just to give a perspective, this is a star called Betelgeuse, which is brightly visible in the sky in Orion. Even today, if you have a clear sky, you go out and look at Orion, Betelgeuse you can see. That star was not there when dinosaurs were here, because it was born 10 million years ago. Dinosaurs were there 65 million years ago. And so all these say this is a red dusty star, because now it is a red supergiant, and they are producing a lot of dust. Now sun is moving through it, and if there are interstellar medium which is dusty, those dust is falling on us, and we have those on Earth as well. And you can actually hold them. This is in our lab in Copenhagen. This was a particle of a meteorite which has fallen, and if you make a cross section of it, you will be able to see the isotopic ratios, which matches with whatever I was talking about, supernovae or other stellar sources. You can actually analyze it to find out what the source was. And it is well understood what type of sources we are expecting, because if you look at the periodic table, you see this is a very interesting image where different, you see what type of elements are produced in what type of astrophysical sources, because at Big Bang you only had hydrogen, helium, and a little bit of lithium, and then you had produced all these elements. Some of them can not be produced in stellar surfaces, but most of them are. And you see at the exploding massive stars are the major contributor of oxygen, fluorine, neon, aluminium, silicon, sulfur, and also a lot of iron, cobalt. All these things comes from massive stars. Whatever is present today in the room, the oxygen you are using today to breathe, those all have come from some kind of massive stars that was present somewhere, sometime. So because of that, you can actually relate by the isotopic ratios that what is this planet made of, were our planet, like parents, what was here before sun was present. All those things you can, I mean, make a hypothesis of based on the isotopes that you see from the pre-solar particles that you can collect from different sources. So way back to again what was happening. So this is the elemental like inventory that we have. We have a star, the star exploded, everything that was present in the inside the star, it gives it like, take now, all these materials are for you to use. But what will you do with that? So once the star has exploded, again I will explain it even a little bit more, but say these stars has exploded and there are silicon, oxygen, magnesium, all these elements I was showing. Say they go through a series of chemical reactions, and those chemical reactions lead to production of different chemical compounds. This is a network of gas phase reactions and coagulation, condensation. All these things come together to finally end up producing micron sized particles, and this happens with like a lot of chemical barriers that we can expect. So this is an example of a simulation where you have a cluster of carbon particles. Everything is carbon. Now there are infalling particles of hydrogen, oxygen, carbon, H2 molecule and CO molecule, and you can actually simulate how many particles form bond on the surface and how many particles are actually repulsed away, and based on that you can actually trace the evolution of these grains over the size. This is still not a dust particle to tell you. Even if it looks like there are millions of atoms there, this still is a molecule, and you have to grow it even further and further to have it act like a solid particles. And this simulation, through which you can actually try to find out what would be the chemical structure of those particles which will form the dust grains in a given way. So I mean, I'll try to make it like simple. I mean, there are, you can do it for different type of chemical composition. So these are carbon based particles, these are oxygen based particles, and these all are produced in both space, and you can actually do them in simulations as well. And once they grow through considerable size, they go through coagulation and accretion, and then you form things like that which you actually see in the interstellar medium. You don't see this in stellar surfaces because stellar surfaces are too hot to, not surfaces like winds, stellar winds are still too hot to have ice on the surface. But when these particles go to the interstellar medium and temperatures are below 50 30 Kelvin, you see particles like that which has a ice of CO2 water on the surface of the dust grains. These are the entire evolution of things that came out of the star and they have gone to the interstellar medium. So they can be anywhere in close to a micron size, like sub-micron, 0.5 micron sizes that grow in the interstellar medium. In the stellar medium. In the interstellar medium also there are grains of almost similar size, but they get reprocessed many times. So the chemical like texture changes. But what happens is they grow in the interstellar medium, but then again they break down and then again grow. So the grain sizes almost remain same, but the chemical composition and the structure changes in the interstellar medium. Close to, yeah, but hot as in you need time for that. You do not produce it on day immediately. You need time and because the velocities are like a few thousand kilometers, so within a year your gas will be close to a parsec away, or like within a few years your everything that was present inside the star is now close to a parsec away from the center. So it is now, there is actually opposite problem that it becomes too cold very quickly because it is expanding with yeah, I mean shock happens in the outer parts more when there are a lot of physics that is there, and I will have to be fast because I've not yet reached any science part, still the introduction of the theory. Yeah, so again, I mean, but still I like to quickly say, so why I'm saying dust, molecule, this, that, from a basic atomic physics that you study in like BSc, MSc, what happens is when you have electronic transitions. You see discrete lines coming out because they are representative of the energy levels of that compound. Now we have a chemical compound which is large in size. What does that mean? It means that all possible like bonds between those atoms are present in there, and so when you are having a transition coming out from these solid particles, you are having transitions for all possible energy levels because all possible energy levels are present in there. So instead of having discrete lines, solid particles end up giving you a continuum emission or absorption because all possible bonds averages out and gives you a continuous distribution of energy levels that leads to a continuous distribution of absorption and emission features. And mostly this happens in the infrared region. Why? Because infrared is thermal radiation. If you heat it too much, say I take a rock here and I keep on hitting it, once it becomes hot enough, it will start, its radiation will be represented by its temperature. So that is the thermal radiation, and the transition that is happening because of the radiation is in the vibrational bands and rotational vibrational bands between the atom. If we heat it even further, what will happen? They will start evaporating and ionizing partly. Then those transitions will relate to the electronic transitions between the levels, which do not happen in solid particles. So all solid particles mostly represent thermal radiation because when you heat up something, all the bonds present inside, all the energy levels, they have the vibrations in their bonds, and that leads to the transitions that is known as thermal radiation, and that is the characteristics of any solid particle. Inside the room also, you take a rock, you take this table, it is the same. If you take the spectra of this table, it will give you exactly the same, the thermal radiation coming out of this table. So this is what differentiates a solid particle with a a gas particle with a dust particle. Okay. So what type of then absorption, emission, whatever I am talking about is expected. For simplicity, let us assume there are mostly two types of these particles present in space. One is oxygen based, one is carbon based, because I mean, I should have put another slide to it, but the main driving factor is the CO molecules, carbon monoxide molecules. Carbon monoxide is the most stable molecule present in these environments, and because of carbon monoxide, what happens is that if you have more carbon, it will produce it will take up all the oxygen. If you have more oxygen, it will take up all the carbon. So most of the time you will see predominance of carbon based dust clusters, or you will see oxygen based dust clusters. You hardly see both of them together because of the presence of carbon monoxide molecule, which does amazing thing that it becomes the most reactant species in space. And so either you form oxygen rich clusters or you form carbon rich clusters. How do we differentiate them? Briefly, so these are the rate of absorption or emission that I am showing. So this is something called absorption coefficient, which is like basically a representation of opacity of a medium. And this opacity of a medium, you can measure it in the laboratory, how much it can scatter, how much it can absorb. Same for a carbon based compound and a oxygen based compound. And one of the way to differentiate, there are many ways to differentiate the two. In a spectrum, one of the way of differentiating is this feature you see in oxygen based compounds, which comes from the bond of silicon and oxygen. There are two types of bonds that it forms even in this structure, and because there are a lot of these silicon oxygen and oxygen triple bond, you see these clear features which are also called silicate features in astronomy, and presence of this feature in the spectrum is a clear marker of differentiation between oxygen rich medium and a carbon rich medium. Okay, so if we now summarize all that chemistry in a life cycle of a star, this is a life cycle of a star. I am like supposed to talk about massive stars, which go through phases of its main sequence, as I said, and then it becomes red supergiant, and then it explodes as supernovae. Okay, if we look at the population of stars in our galaxy, this is the same HR diagram in a more complex way. This is your main sequence line, and these are your evolved stars. You see blue supergiants, yellow supergiants, red supergiants, and Wolf-Rayet stars. Wolf-Rayet stars are hot. these are colder, this is the temperature line, this is colder, this is hotter. So these are the colder evolved stars, this is a hotter evolved star, and these are present in the LMC, which is a neighboring galaxy, large Magellanic Cloud, and these are the stars present there. Okay, so what does these stars do in the end of their lives? There are different, I am talking about it from a theoretical perspective. So once these massive stars reaches their end of their lives, they evolve in a very erratic way. We do not fully understand. So one of the theories that is being developed is how does these evolved stars pulsate near its end of its life. And there are different phases of pulsation that these massive stars go through. One is that based on the luminosity to mass ratio, what happens is once the star becomes too large, the outer bound of these stars, these regions, becomes unbound because it is gravitationally unstable to have such a large star. The outer parts of the star becomes unbound and they are driven away by the radiation. Now, once you drive away the gas from the outer surface of the star, what happens is this mass decreases. So in the L by M ratio, luminosity to mass ratio, the mass of the star decreases. So L by M ratio increases. So you will have more luminosity to mass ratio that leads to even heavier pulsations, and these heavier pulsations leads to even more mass loss. So this is a theory still. There are a lot of hypotheses going on to actually test that. But once these high mass loss rate comes in, like how stars are losing mass by pulsating, you can actually create a series of processes that leads to enhanced mass loss in the end phase of these stars. What is that? So this is an observational evidence of, if you look at supernovae of different types. Why supernovae? Because even if stars were doing that, we were not able to see them. Those are far away sources. But once those stars die as supernovae, they are bright sources. So we actually see whatever is present around it. Okay, so once we try to probe what is present around those stars, we can see evidences of high mass loss phases that this star has gone through. So what this picture is, different supernovae that has happened in last 15 years. And in that 15 years, there are stars which has lost mass at a very high rate. 10 to the power minus 4 to minus 3 means in 1000 years, it will be able to lose 1 solar mass of gas, which is like our sun's mass. So it can lose a lot of its mass by winds near the end of their life. So the theory is developed on how these stars are losing mass based on an empirical formulation of mass loss rate given by a power law times a standard physical prescription. And from there, you can actually determine the rate at which a star will lose mass that matches with the environment of the star. Why I am pushing towards it, maybe I have not been that clear, but that mass loss becomes extremely important for two phases. One is that observational evidence of these stellar environments, and two is that to form dust you need to have high densities. So a lot of these stars which are dusty, like Betelgeuse, I gave an example, those stars, without this high mass loss, we would never be able to see those dusty stars, or actually dust would not have been present. So the fact that these stars are very dusty is one of the reason that we need to have high mass loss. Plus, if you look at these stars in any other wavelengths, I mean stars or post-explosion remnants of those stars, you will see in X-rays that the medium is very dense. Like this is an X-ray image. And in the X-ray, you will see that the medium around the star was much denser than you can actually explain by basic physics that we know. So the theory is on how you can produce a mass loss that mimics what you see in these stars. So this is a theoretical explanation of, if you take 15, 16, 17 and 18, 4 stars, you will see that how the rate of mass the star will lose. This x-axis is the time in a reverse scale. So 0 or minus 2 is basically when the star died. Okay, and this is the years in log scale from time before explosion, and this is the rate at which the star is losing mass. So if you see 15 solar mass star will have hardly any mechanism to create these eruptions before it explodes. If you look at a 18 solar mass star, you see that 0 to 1 means 10 years from the time of explosion. In the last 10 years, it has gone through these phases of very enhanced mass loss, which is theoretically unique because we have seen evidences of that, but we have not found a theory which explains how a star would be able to have these eruptions right before it explodes, in the last 10 years before it explodes. Yeah.
Star, you see in 18 or even I think
Yeah.
16 also there are some
Yeah, yeah.
What is the physics that there should be some threshold mass, or is just because of the modeling that you have a, because I would expect this to be a continuum thing, possibly that
Yeah.
you have the higher the mass, you have more and more mass loss, while as you go to the lower threshold, you have less and less of it. But then in this figure that you are showing, is it just a theoretical thing that it could be cut off, or is there a very strong physical reason that you wouldn't see in 15 and you see in 16?
No, the theoretical, there is some theoretical cutoff, but it is based on what you see the in observation. What you see in observation is that only stars which has like a very high very high, not very high mass, but which are relatively close to 20 have been seen to have these eruptions before explosion. On the other hand, if you go to lower and lower masses, they have no mechanism to produce this. But in theory, what is done is that it is all based on the luminosity to mass relation, and these stars, even if you have mass loss, they never reach the critical L by M ratios, which triggers the eruptions that happens in the end phase. While more and more high you go, actually there is even more to it. If I go to 19 and 20, we are again back to a different scenario where this is the helium burning phase, and most of these stars create these eruptions in the helium burning phase and then becomes almost like a nascent star after that. So this is the critical region of 16, 17, 18 and 19 where you see these eruptions. Post 19, the 2021, they often do not go through this phase, and there is another theoretical aspect which studies that these stars may actually not explode but implode as a black hole immediately once it will go through the late phase. It do not reach the condition to explode, so they would implode and become a black hole directly from there. So these 4-5 solar masses, 15, 16, 17, 18 are the critical region where you will see these like interesting facts happening. Yeah. So one of them is like, say, the luminosity mass ratios, as I was explaining.
What is the no, there are these at certain masses related to certain inner core temperature, then in some cases the radiation pressure becomes important. In some cases the free scattering is not so important. All those things are also related to the opacity of the medium.
Yeah.
So you have to given the metallicity of
So so these are, I am showing for solar metallicity cases. If you change the metallicity, this picture will completely change. Yeah, but again, these are, I am saying so easily luminosity mass ratios because in a modeling it is done still in an empirical way, where in the luminosity mass ratio we make the theory to derive the this kind of observed scenarios that we see. But if you actually want to make this happen through evolution, you have to go through this. Yeah, metallicity, rotation, all these things impact it. I am showing about non-rotating single stars of solar metallicity. If you change those condition, again a different picture will come up. Yeah.
But not solving the stellar structure equation.
I am solving in this model, we are solving it, but in all these stellar structure, stellar evolution methods, there is no theory which actually inherently produces the mass loss prescription. You have to tell it. You have to tell it how to produce that. Yeah, you have to lose
some value, threshold value, and after which
it would create these things. Yeah. So the theory is there, but where to actually lose the mass, that you have to still define in your way. It does not inherently create the mass loss.
Like MESA or something, will that?
Yeah. These are all done with two models, one MESA and one called Kepler. which is Stan Ousley and all these people's code. So they are done both, and they have some differences, but this phenomena is similar, that you have this critical stellar mass where you would see this feature, and these are always observationally motivated, that there is this thing called red supergiant problem, where you don't see any red supergiant above 20 solar mass. You have never seen them. So that accounts for how it will evolve in how these stars will evolve in the late phases of their
But
life.
that doesn't produce any sort of the pressure at the outer surface, non-zero pressure, and how much non-zero it will be. That kind of information you can get from.
Yeah. I mean, so the parameterization is happening based on those informations that you put. The informations are there, but then you have to still tell that, okay, when these conditions are met, then you will have the mass loss there. So that is what it is made. If the yeah. So this is like an exponent of the power law. That is again parameter. I mean, in the paper we had to parameterize it for different. So these relation, yeah. So this is like one prescription from 1988 derived from observation. But then there are more theories which defines that, okay, so in certain cases you will have enhanced pulsation, and those pulsations can be modeled by this eta times alpha, where alpha is a constant and eta is the mass luminosity factor that comes out, and these pulsations are like different in different mass stars. That is the empirical prescription, but the prescription is defining how much eruption you can have or cannot have in certain stars. Yeah.
Since you have shown that, yes.
Yeah.
So this is the X-ray profile, correct?
This one, yeah.
So have the eruption, single burst kind of. The X-ray profile should show that up.
It would, but these are all post-explosion things. Okay, eruptions are. It will still. Yeah. You can. If you have a very good cadence, you will be able to see that. Yeah, most of the time it is all mixed up, and what happens is those eruptions happen within last 10-20 years. Okay, supernova sweeps that in like 10 days. After the supernova explodes, within 10-20 days all this material is gone. So unless you have been observing it every day for since it explodes, cannot find that clear evidence. Those are the challenges that you have. But nowadays, with so many detections, you will see more and more objects like that. Okay, so once these stars actually evolve, and nowadays we do have tools to study those. If you look at red supergiants to probe what is in the environment like, say JWST recently has found many of the dusty red supergiants, which is unique. We did not have as many before, just because we did not have the tools to study them. So there are two recent papers which has found out very large amount of infrared emission coming from the progenitors of two of these stars. This is 2023 IXF, which is one of the closest supernovae found until lately. Closest means still 5 megaparsec, but that is one of the closest one we have recently found out, and 2025 PHT. Both of these JWST images are showing bright infrared emission, which represents that these environments surrounding the star is dusty. So the theory that I am talking about would not only create this eruption, pulsation, heavy mass loss, but also in that wind, applying all these chemistry I talked about, you will be able to condense the dust grains. And by modeling again, we see how dust would grow. Here we have silicate dust, because as I explained that either you have oxygen rich environment or you have carbon rich environment. Most of the winds are coming from the outer envelopes of the star, where you have oxygen to carbon ratio is more than 1, which means oxygen is more, and so you will predominantly have oxygen rich molecules and clusters. And if you look at the evolution of silicate dust, you will see as a distance of the star at different time before the core collapse, how much dust you would be having in the medium, and then what would be its infrared fluxes. So these are the fluxes that I showed in the previous slides, and then you can model them. I mean, I do not want to show the every details, but this is the star. The blue line is actually the star, and then the star got attenuated here. And then that attenuated means what? The gas surrounding it has absorbed it and then re-radiated back in the infrared wavelengths. And these are the features of infrared radiation that you will see, comparing it with the previous slide I showed, that there are observational evidence of dusty red supergiants. Terribly late in time, but so
you have, say, 10 minutes. Is that 10 minutes or
more, you mean?
Yeah.
I would be able to, I think, reach a good state. It's fine to go 10 more minutes. Okay. Okay, so I'll try to make it fast as much possible. So these stars have not yet exploded.
Okay.
Yeah.
Particularly with us.
Yes. So see, these stars now would be able to explode, because I was right in last 10 years before the explosion. So now these stars explodes, and what we have in a very cartoon picture, this was before. Star, some medium, something dusty, I was explaining, because the medium can be dusty. Then you have a star exploded. This is a supernova remnant, stellar remnant, which is most of the time a neutron star. Then you have the ejecta, which is metal rich, and then you have a forward shock moving outwards through that medium and a reverse shock coming backwards. This forward shock reverse shock picture becomes more important when the medium is dense. If the medium is not dense at all, then this is just a forward shock moving outwards, and the metal rich part of the star is just expanding outwards. So all these regions A, B and C, A was already here, which was already dusty. B and C are also very ideal conditions to form these dust grains, and I'll briefly go through like what happens. So all the massive stars, even if I have not able to explain all that, have a structure like onion shell, which has different metals. Our outer part is hydrogen, and then helium, then carbon, oxygen, silicon, like layering like that. So once the star explodes, some of these layers get mixed, but some of them actually maintains its structure and they expand outwards, and there is a lot of radioactive processes that is present because of the presence of nickel 56, which is the radioactive species produced at the time of explosion. So because of this presence of radioactivity, you have a lot of gamma rays, and the gamma rays deposit the energy in that gas, and overall the evolution changes because the gas is expanding very fast. So whatever chemistry I was talking about happens in this race against time, that the fast evolving ejecta goes through a decrease in temperature and then a decrease in density as well. So you have to form molecules and dust. By the time the density becomes too low, before the time the density becomes too low, and the temperatures are almost appropriate. So I will not talk about the exact results, but this is the distribution of how much dust you form in different parts of the supernova ejecta in a velocity space. And to point out to that onion cell-like structure, if you look at a 15 solar mass star, it's stratified ejecta. This is the outer hydrogen layer, this is the helium, this is oxygen, and this is more silicon-rich layers. So the layered structures that you had before the explosion, after the star explodes, most of the time it maintains that layered structure. And so based on the abundances of elements in different parts of the star, you see this is the inner metal rich part. Why I was saying metal rich, because of this onion cell like structure, the inner parts of the star is very metal rich, made up of oxygen, silicon and carbon and stuff like that. And so these are the primary elements that form dust. So once you have this gas, you will be able to condense a lot of lot of these elements to dust grains. And so the metal rich part, this part which is in mass coordinate space, say within 4 solar mass of the star, this was a 15 solar mass star. So the outer part is all hydrogen, but inner parts you have a metal rich core, which is very convenient to produces conditions very convenient to form dust. Okay, so this is where you actually have some observational signature. I was talking about infrared lines coming from dust, but infrared is not the only one. What happens more is that because of the high velocities of these of these stars, you get a very strong broadening. Like if you look at the line profiles of hydrogen, if you assume like a broad profile where this is the zero velocity, what happens is you have a very broad profile. Okay, now you form dust in there. What happens is you had this whole entire structure. Now you have formed dust over here. So what happens is the light coming towards you get partially blocked. The light comes from here more and from here less. So this line profile will get shifted slowly towards the blue side, because the light coming towards you will be more, light coming going away from you will be reduced. So by just looking at the asymmetry of the lines in the red side and the blue side, you can measure how much dust you can produce in the gas. Why it is unique? Because you do not need infrared observation, which is difficult to make, and it can happen even at late times if you have H alpha or any of the lines coming out. And that is why this finding is unique, and you can actually measure how much dust you form just looking at the optical lines. So I would finish here, based on, the summary. So all these stars I was talking about, different solar masses. If you take these models of all stars coming from 10, 20, 30, 40, how much dust they can produce, what we can find is there is a large amount of stochasticity. You see there are so many peaks. What I am plotting is that how much of carbon rich dust, how much of silicate rich dust, basically oxygen rich dust, you can produce in different progenitors. And if you see, there is a large amount of stochasticity that is coming from the large variation in silicon and magnesium ratios that the star has produced inside, and we do not understand how. So actually we have written a grant this year which was motivated by this idea that we actually really want to understand how these silicon magnesium ratios in different progenitor masses varies to such a large extent. And this can be only studied when the star exploded and gave those material out to you, because before that the star was doing whatever it wants to do. We never see it. Once the star explodes and all this material has now come out, looking at the features in dust, we can actually find out how much ratio of silicon and magnesium it has produced. And we find that at least theoretically there is a very large stochasticity in that kind. There is basically random numbers of how much silicon and magnesium you could end up with. Okay, so since I promised that bit of JWST data, I'll say that, like, say I am a theorist, so my motivation is to find out why all these things happen. So summing up all the like supernova that has been observed, there are a lot of data that we had until 1000 days of the explosion. Then at late times, there are only 2-3 supernova remnants that we had studied. In the entire period between 1000 to 100,000 days, we almost had no data. And so how the star is evolving, like how much dust they would have formed, we never knew. JWST actually had that proper tools to study the evolution. There was a mismatch between how much we thought as theorists, which always predict that any supernovae is very metal rich, very dense, they will be able to produce a lot of dust initially. But observers always found that there is a very gradual growth which goes for thousands and thousands of years on the mass of dust. We could not match that, and JWST has the tools to actually resolve this. When the first supernova was observed with JWST, I was part of that paper where it was came out in all the news and all. Eventually, actually, even Anandabazar Potrika has covered that news. So we actually detected a 25-year-old, 20-year-old supernovae, which is glowing in mid-infrared. And we had developed all the modeling and theoretical aspects of how we can find dust emission in objects like that. And there are now around 15 supernovae. These are evidence of 2 more. There are now 15 supernovae coming from these 6-7 cycles that we have. And I mean, I am part of most of these as a co-I. And these are the ongoing cycles which all are motivated to find out supernova dust, to find out actually how much dust supernova can produce. So I will not say much. So this is okay. So this is now ending with Wolf-Rayet stars, because I had to say about massive stars, and Wolf-Rayet is a unique case. Why? Because it is much hotter than all others. Because they were cold, I could argue that okay, they have temperature to form dust, but Wolf-Rayet stars are much hot. So they form dust by the colliding wind of these scenarios. You see, these are 2 stars which are colliding, and then they produce regions in this boundary of this collision where you have enough condition to condense molecules and clusters. And so finally, this is a famous image of JWST ultralight 140, and we are trying to model how much of the molecules and dust you form in these rings based on the aphestron and periastron, which so basically perihelion aphelion is for sun, periastron aphestron is for stars. So based on how close they are in this binary interaction, that how much dust you could produce. This is the image of that, and this replicates this ring-like structure that you see in ultralight 140 with all the chemistry that I talked about. That's all. I had overshoot a few minutes at least, but thanks a lot.
Okay, questions, comments, critiques, praises? No question. Okay.
Yeah.
The first question is that we discussed a lot about the formation of dust, and then how dust exists in the galaxy. But once it exists in a galaxy, how does it evolve and how does the distribution change with the galaxy there? That's what I want to.
Yeah, so that is like a complete another picture of what happens. So in the galaxy, there would be a lot of turbulent processes that the molecular clouds go through. There would be shock waves that would bring the clouds together, that can initiate a star formation like phase as well. And then on the other hand, it can also destroy stuff there. The grain sizes, so since the silicon, carbon, all that thing I'm talking about, they have a relative difference of how they will be processed when you have turbulences or high energy radiations coming in. Different grains will act differently. Their grain sizes will evolve differently according to that as well.
Can I continue?
Is there anyone else asking question? Okay, Paula's.
Yeah.
That figure of where ultralight stars, lightning
Right, yeah.
the ring-like structures that you showed, is it a simulation or a real?
This is a real image. This is simulation. But yeah, this is like a picture taken by JWST. Yeah, so that is the mystery. I mean, ring-like structure is coming because they are binary stars moving around each other, and they are coming close. They are coming close and then going away. And these are dusty lanes. So these are around 17 dusty lanes present, and these dusty lanes are produced when they are close, and then when they go away, you do not have dust. So you have periods of no dust formation, then high dust formation, and that leads to this ring-like structure produced in these ultralight stars. I mean, and these are winds. Basically, once these stars are coming close, they will have those wings these regions become denser when they come close, and then you will have conditions to produce molecules and dust. When they go far out, they will not have that conditions conducive to form dust.
And in another one, you showed the silicon to magnesium ratio.
Yeah. So that is like unknown. We do not know. We have tried to see if it was a computational effect or it is real. So there are 3D simulations, 1D simulation, all forms. All these stars end up with a random distribution of heavy elements which have some theory, some understanding, but it's not a clear picture that why a 15 solar mass and a 15.2 solar mass would behave very differently in evolution, and these abundances of heavy elements, and we want to understand it even more. And the dust connection is because these things only are visible when they have exploded, because otherwise it was inside the star and we would actually not know how much of what is happening, all these nuclear processes is happening. So this part is theoretical, but theoretical models have been looking at it for many years, and we still have a very randomness on the heavy elements that a star would be able to produce. Yeah, so I mean, we have have a proposal, I mean, a grant to study in detail this feature, how much of it is a computational effect and how much is it a realistic effect, and what is the connection of this stochasticity of the heavy elements produced inside the star, like the randomness, is it real or can that be confirmed from observational sources? That is something we want to study in more clear picture. Yeah.
Okay. Is that
My next question is that in the very initial part of the talk,
Hmm.
you were kind of hinting at the very early galaxies are dust, right? So again, it kind of hints that supernova explosion that we said did not happen. So since the fact that cause of reionization is even more in debate due to KWST finding newer galaxies, can this kind of put a constraint on what, well, like if supernova and other stuff, the ratio of how much did one affect reionization than the other? Can we put a constraint just by looking at the dust data and the processes that are completed?
Yeah, definitely you can. Well, JWST is not literally finding dust in those galaxies because those are redshifted emission. So you can produce some hints on the galaxy evolution of the earliest galaxies based on what we know. That has already been done. I don't particularly know how much JWST's finding has changed that picture, but we do have some understanding on the evolution and the initial mass functions of the earliest stars. Initial mass functions is that, like, what is the distribution of masses of those stars? That we have some constraints based on what we see in dust.
okay? Other questions?
Hmm.
Just clarification is that you are generally talking about oxygen rich and carbon rich things, but you mentioned it's, as I also understood, it's carbon and silicon. So the silicate is the synonym.
Yeah. Almost when say a lot of oxygen rich materials are all silicon oxygen compounds. So that's why I made it more synonymous. But yeah, there can be other oxygen rich, say iron oxygen compounds and aluminum oxygen compounds. They can also be present, but most of the time we see silicon oxygen complexes to be present. So I was kind of labeling them as oxygen rich. While carbon itself has this amazing structure of forming bonds among itself. So a lot of carbon is in pure form. Like it can be diamonds, it can be graphite, it can be just like clumps of carbon, but carbon itself can form large clusters of its own. So it is carbon, and then you have carbons. Oxygen cannot do it by itself, so it form bonds with other species like silicon and magnesium and stuff.
Supernova observations for local that